This diagram shows the physical forces inside a cylindrical column of water. If you've ever touched the bottom of the deep end in a swimming pool, you've felt this exact model pressing against your ears. The deeper you go, the heavier the water above you becomes. That physical sensation is mathematically defined by the hydrostatic law. The pressure at any given depth is the fluid's density times gravity times the vertical height of the fluid column above it. P equals rho GH. But water in a pool is open to the air. When you trap a fluid inside a closed container, the rules shift. According to Pascal's law, if you apply pressure to an enclosed static fluid, that pressure is transmitted equally and undiminished in every possible direction. This principle dictates how we design heavy machinery. Inside a hydraulic jack like this one, a small downward push on a narrow piston creates uniform pressure in the trapped oil. Because that exact same pressure pushes upward against a much wider base, the output force is multiplied, allowing a single person to lift a vehicle. Before calculating these forces in the field, we have to establish our starting baseline. The true bottom of the scale is absolute zero pressure, a perfect vacuum where no molecules exist to exert any force. Because we live under a heavy atmosphere, we are constantly subjected to atmospheric pressure. Engineers use this atmospheric baseline as the practical zero for their instruments. Any pressure we measure above this line is called gauge pressure. If a system's internal pressure drops below the atmospheric baseline, it registers as a negative gauge value, physically known as vacuum pressure. Failing to separate the absolute zero line from the atmospheric baseline is the most common reason students drop points on their exams. To measure gauge pressure inside an active pipe, engineers start with the simplest tool available. This diagram shows a piezometer, a vertical tube physically tapped into a pipeline. The fluid simply rises up the tube until its standing weight balances the internal pressure. But this setup has two strict limitations. Because the tube is open to the air, it cannot measure gas, it would just vent out. And for high-pressure water, the liquid would shoot right out unless the glass tube was built several stories high. To solve this, we bend the glass into a U-shape. We fill this bend with a completely different, much heavier measuring fluid, like mercury. Because mercury is extremely dense, it drastically condenses the physical height needed to take a reading. A very small vertical shift in mercury balances out a massive pressure spike in the primary pipe. When reading these instruments, you must extract a balanced mathematical equation from the physical fluid levels. You can use the jumping method, tracking pressure continuously from end to end, or the left-right limb method, isolating the two halves of the tube. Both methods rely on unbreakable rules. First, locate the lowest interface where two different fluids touch. Draw a horizontal datum line exactly here. Because pressure in the same continuous fluid is equal, pressure at both points on this line is mathematically identical. Next, evaluate the fluid columns above that line. Moving downward through a fluid adds pressure, so you use positive rho GH. Moving upward subtracts pressure, so you use negative rho GH. Let's test this instantly. This schematic shows a differential manometer comparing an oil pipe to a water pipe using a mercury bend. Grab some paper, pause the video, and write out the balancing equation using the datum rules we just established. Sometimes engineers need to measure very slight pressure differences between two pipes. This diagram shows an inverted U-tube manometer, which solves this by using a very light fluid, like trapped air, at the top of the bend instead of a heavy liquid at the bottom. This setup introduces a specific trap. Because the measuring fluid is trapped at the top, our standard datum rule flips. You must draw your reference line at the highest contact point between the liquids, not the lowest. Let's check your work on that active recall problem using the left-right limb method. The total downward pressure on the left side of the datum equals the downward pressure on the right side. You add the pipe pressure to the weight of the oil column and set it equal to the opposite pipe pressure plus the mercury column. The algebra is straightforward, but exams hide two strict traps. First, they give you the oil's specific gravity, not its actual density. To use it in the equation, multiply that 0.9 by the density of water to get 900 kilograms per cubic meter. Second, secure your units. The differential height is given in centimeters, but standard gravity requires meters per second squared. You must convert those centimeters into meters before multiplying, or your final output will be off by a massive factor. These mechanics form the core of fluid pressure measurement. We've compiled the essential frameworks, from the absolute baseline formula and hydrostatic law to the directional rules and datum placement, into a single cheat sheet. Memorizing formulas will only get you so far. By internalizing exactly how these fluids push against each other physically, you will reliably navigate any pressure network the exam throws at you.